Okay, so we have talked a lot about input modeling and so on, and so now we're starting to move into actually focusing on the output and comparing your simulations to the real life and to validate them as well as simulations to each other. So, but before we get to that, sort of focus here. So, like this week's lab, for example, you'll be focusing on the output analyzer, which is a tool in Arena that helps you to rigorously analyze in a statistically rigorous way the outputs of your sims. So again, you can compare them to each other or compare them to real life. If you're already familiar with tools like JUMP or SPSS, SAS, R, then the facilities in the output analyzer and really in the input modeling tool are pretty rudimentary, but they're just sort of the basics to get you going. A lot of what we'll learn about in the next unit about when we talk about relative performance, the confidence intervals that come out of the Crystal Reports tool will actually be enough for a lot of the types of comparisons that we do. And then in Lab 10, some advanced topics, things like batching, signals, and holds, some really cool things that you can do with a couple of these tools in Lab 10. Lab 10, again, will be even though it's graded out of 30, there'll be 50 points possible. So it's because it's your last lab, I give you this opportunity to try to learn a little bit more about Arena and get some basically almost like half a lab or almost a full lab bonus credit out of it. So I recommend taking a look at that. You don't necessarily have to take advantage of all of that, but if you're looking to bring your lab score up, then that's a great way to do it through the bonus credit on Lab 10. Otherwise, the rest of the semester's lab slots basically view as final project slots. So you have plenty of time to work with each other and to get help on getting your final projects in good shape. So the final project, again, 20% of the final grade. You guys know all this stuff by now. The next, the input modeling feedback report, thanks for turning all those in. I got them back from all the groups. That's great. I now have to go through the process of reviewing them all and giving you feedback. And I will do that as soon as possible. But just keep moving forward, assuming everything's all right while you're waiting for that feedback from me. The next deliverables will be the presentation video and the final report, but that's not until the final week of classes in the middle of that week. And then once you submit those, then the Saturday before finals week, then your peer reviews of another group's presentation and another group's final report will be due. So that's kind of what's due in the type of kind of applied side of things. On the other side of things, in the kind of lecture side, we've got a couple more ICAs available before the final review ICA. Homework G3 is still out. It's been out for a long time, but it's due soon. So we'll give you kind of the last hint in this lecture on how to do part 2 or question 2 if you're still having trouble with that. Otherwise, there are videos on Canvas for help with the power analysis. And then after that homework, then the last homework is homework J2, which will be an Arena-based assignment. It will be based off of an inventory management problem that you've seen before in labs, the kind of whatever the Bucky's inventory system or something like that. And so we'll ask you to do some modifications and some test runs and sort of applying a lot of the things that we've been talking about and then trying to make inferences. So that's kind of what's coming up. Any questions about the schedule? Check online too. Any questions? Okay. Great. All right. So, like I was saying, we've been talking about input modeling and we're gradually transitioning to output, and there is statistical overlap between that. A lot of stats in this start of the semester. So hoping that you're feeling more and more comfortable with things like type 1 error, type 2 error, power, and like, graphs like these. So if I show you, a null hypothesis distribution of outcomes, an alternative hypothesis distribution of outcomes, a threshold, that you'll be able to map a picture like this into these 4 error rates, or 4 not error rates, but kind of where inferences land: false positives, true negatives, and false negatives. And as you move this threshold to the left and right, I hope you can see that if you were to plot type 1 error against statistical power, as you would in an ROC curve, then every hypothesis test will etch out a kind of bow like this one here. or really bad hypothesis tests will be close to the diagonal, which basically just mean that you flip a weighted coin and that's your inference. But a really good hypothesis test will be close to sort of a right angle where it'll go up this way and come up this way. So the fundamental thing that's captured here is as you increase your type 1 error, you also increase your statistical power. Or in order to get more statistical power in the same test, it often means also the trade-off being you're going to get more type 1 error. So ideally you switch to a more powerful test because you want to have the same type 1 error, but you want more power. So that's why you might go from a chi-squared test to a Kolmogorov-Smirnov test. And why would you want more power? You typically seek statistical power when you're looking for some sort of confirmation of a null hypothesis. If all you're looking to is to reject a null, and you've successfully, if that's the right term, rejected it, then there's no reason to think you needed more power. So power is how we sort of confirm that we're not a null. And because if you don't have a lot of power and you don't reject a hypothesis, it might just be that you didn't have enough samples. And so that's kind of when you sort of start to get more of an intuition about what we mean by power and so on. If we focus on particular tests, like the t-test, I gave the history for the t-test last time. It's a simple expression here. You take a bunch of data and you take the average of those data, and that average becomes a so-called one sample that you're going to be testing against a hypothetical average. And then this expression here is the so-called one sample t-test. So the average from your data minus the hypothetical average divided by an estimated standard deviation that you also have to estimate from data, and divided by square root of n. And we learned that the reason this is structured this way, as we'll see graphically here in a second, is that this is effectively a z-score. It's a standardized error. It's saying that this is the average I got from my data. This is the population average of my null. I'm going to take the difference between the two of them, and I'm going to standardize them by the so-called standard error of the mean. And that's what the denominator is, the SEM. And that is if every time you did the experiment over again and recalculated this y bar, this average up top, this arithmetic mean, you would get a different value. And the standard error of the distribution of the y bar values is what's being divided by down here. So it creates a type of a z-score. And if you have a large number of samples, it is exactly a z-score. But the t-test is for you when you have a small number of samples. It allows you to do a z-score-like inference with only a few samples, like 10 data points or something like that. So you can start detecting differences so this is more, it has more power. So it has more ability to detect differences with small numbers of samples. Now, what gives this more power, in part, is the fact that you assume that these data are normally distributed, and you assume that if the data are from an alternative hypothesis, they have the same standard deviation as the null hypothesis. So you make a lot of assumptions, and on top of that, you assume that from your data points, all your data points are independent. You need all three of those things to allow you to use a t-test. And if you have all three of those things, you get a pretty high-powered test. So how does this t-test work? Here's a t-distribution for a number of different degrees of freedom. The degrees of freedom are basically the number of data points that went into calculating that average, that y bar. So 1 degree of freedom means there were 2 data points, 2 degrees of freedom, and there are 3, and so on and so forth. And so as the degrees of freedom gets to infinity, then the t-distribution, which has fat tails, gets narrower and narrower tails and gets higher and starts to approach a standard normal. So again, a t-distribution is just a generalized kind of standard normal that works even when you have few numbers of samples calculating that average. And so you use it just like a z-test. So if you get a large t-value out here, it's unlikely to come from the null hypothesis. A small t-value might come from the null hypothesis. So almost always we will use two-tailed t-tests. So that means the critical value in the back of the book is whatever confidence level I give you, significance level I give you, alpha divided by 2. So if I say we want to use a t-test with an alpha of 0.05, you've got to look for the critical value as 0.025. You got to divide the 5% by half, because you're interested in the probability that something is far from the mean in both directions. So it could be here and to the right, or here and to the left. And so both of those tails have to add up to 5%. So the critical value that you look for, if you look in a one-tailed table, which is most of the tables you give you are one-tailed, is not going to be the 5% critical value. It'll be the 2.5% critical value. So that's key to remember there. All right, and so what does that look like a little bit more visually? So here I've got plotted on blue a null hypothesis. So basically I generated a bunch of data from a normal distribution with a known mean. And then I generated a bunch of data with the same standard deviation, but with a mean that's been shifted by 2 units. So it's been shifted to the right by 2 units. And then I calculated t-statistics for both of them. And so the blue one is what we get under the null, and the red one is what we get under the alternative hypothesis that's been shifted over by 2. The dashed line is the critical value relative to the blue curve. So anything to the right of the dashed value represents something that only happens 2.5% of the time. So anything in the tail of this null distribution, that's what we're saying, that these outcomes are so rare that if we ever get data in that area, we're going to call those likely an alternative. So in other words, we're going to reject a null hypothesis. So what we see that for this case, I've taken 4 samples with a standard deviation of 2. And so for 4 samples, then what we see that when we take all of those data and we turn them into a t-statistic, then we see that the null as well as the alternative are pretty darn close together. So in other words, most of the red curve is to the left or to the wrong side of the threshold. So I am going to get, so the only things that are going to come up as positives are going to be things that are also pretty rare in the red curve. So there's going to be a bunch of red outcomes that I'm not going to detect. So they're going to look like nulls. So what I can do, this is because I have very little statistical power. So again, statistical power is about whether you can confirm the null. And this is basically saying that for something that's 2 units away, which I might think is pretty far, a lot of outcomes from the alternative distribution still look like the null. And that's because this is underpowered. So how do I get more power? Well, I can sample more. So instead of going to 4 samples in the next slide here, I went to 20 samples. So if I recalculate my t-distributions for those data, now with 20 samples instead of 4 samples, my null is still centered at 0, but it looks more normal. It gets higher and its tails go down. And then on top of that, the red distribution, the alternative, looks like it moves over. Now, it didn't move over in like real space. Like in our real outcome space, it's still just only 2 units over. But if you look, the distance between these 2 peaks in t-distribution space is this expression here, which is the distance in real space divided by the standard deviation of these 2 curves, which assume to be the same, divided by the square root of n. So as n gets larger, then this distance here gets larger, and this red curve moves away from the blue curve. So the dashed line is still here, but now most of the red curve is in the reject space. So I've increased the power. So I'm now able to detect this 2-unit difference much better when I use 20 samples rather than 4 samples. So that's what's happening when you sample more. You're discriminating, you're pushing these curves apart. And I can do this more. I can go to 30 samples, and now I can see that this red one, like really almost none of it shows up in the null space. And so really this is like great discrimination. Now, if I look at this formula here, the actual distance divided by the square root, or the standard deviation divided by square root of n, increasing sample size is one way I can separate the blue from the red. But the other way I can separate the blue from the red is decreasing standard deviation. Now, or decreasing variance. Now that it might seem like, well, I don't have control over variance. The variance is what the natural world has given me. But I control the experiment. And we'll see in a second how I can design an experiment so that I can reduce output variance. So that regardless of what the actual output variance is, I can somehow explain it away so that the variance that's left over is much less. And if I can manage to decrease the variance in my samples, like on this slide, so now I've gone from a standard deviation of 2 to a standard deviation of 1.5, I can further separate the null from the alternative. And that's what we call variance reduction techniques. And we'll have a whole unit on variance reduction techniques. This is just kind of a preview of that, is how we can either increase samples or decrease variance to give us more power. Now, you have some experience with this on homework G3. So if I go to homework G3, or basically homework G3, I'm not showing the same data in homework G3, but this is basically what you're doing in part 2 of homework G3, is that what we're saying is we have a sim and we have a real world system. And we want the sim to match the real world system. But we've said that as long as they're close enough, we're okay with the sim being a little off. So we basically define, like in the homework, where it's going to say that there's, I don't know, as long as there's a 2 job difference in the job estimates or something like that, then we're considering the simulation to be close enough to the real world system that we don't need to redesign the real world or the sim. So in order to do that, I can feed I can take real world data, and then I can feed simulated, say, customers into my sim. And then I can see, do the outputs of the sim come close enough to the outputs of the real world data? But that's kind of unfair, because the inputs to the real world system were different than the inputs to the simulated system. So already there's going to be a difference in my outputs just due to the slight difference in the inputs. Even if the inputs came from the same distribution, just randomly speaking, I might have gotten lucky in the real world system and got really cooperative customers, and unlucky in the sim and got really difficult customers from the same distribution. So I would like to somehow get rid of the input variance so that the output variance is purely due to the difference between the sim and the real world. So how can I do that? What I can do is I can feed the real input data, not random numbers, into the sim. So I can actually say 100 customers were in the real world data. I can go into Arena and I can say, don't draw 100 random numbers. Here are the 100 interarrival times from the real system for this particular day. I'm going to feed exactly those into the sim. So now it's like comparing oranges to oranges, apples to apples. So I've got exactly the same challenge going into both systems. So now if there's a difference on the output, it really is going to do with the difference in the systems and not an unlucky difference between the inputs. So it puts the same input variation into both systems. And then each sequence of real data is thus going to produce both a real output and a simulated output. Now, because of this, I can't use the standard 2-sample t-test. Because at a 2-sample t-test, I assume that the outputs generated in system A are generated independently from the outputs of system B. So I want to test the hypothesis, did these 2 systems have the same mean? That only works with a 2-sample t-test if the inputs to this system are independent to the inputs of this system. But in this case, every input, like all of Monday's data, generated an output for system A and system B. All of Tuesday's data generated output for system A and system B. So the systems are coupled together. So I cannot use a 2-sample t-test. That's what I'm trying to drive home here, is that I can only use 2-sample t-tests if the 2 outputs I'm testing are generated independently. At the instant they have the same inputs, you can't use a 2-sample t-test. It's just inappropriate, it won't work. But what I can do is subtract the outputs from each other to generate a bunch of differences. And that difference should be equal to 0 on average if these two systems are close enough together. So I'm now testing the hypothesis that the expected value of the difference between real and simulated is equal to 0. And that's the same as the hypothesis from a two-sample t-test that the expected value from the real is equal to the expected value of the simulated. But because I'm generating a single column of data instead of two columns of data, I can now use a one-sample t-test. And a one-sample t-test, by the way, is something that is relatively easy to perform a power analysis on to tell me if I've taken enough data. And so this is sort of the background, the generic background behind what goes on in part 2 of your homework. And this is an example of a paired difference test or a paired difference t-test or a paired t-test. And so this is a more generically what we call statistical blocking, by creating blocks where where two outputs are tied together in a block, and then the next two outputs are tied together in a new block, where every block corresponds to an input that went into both systems. Then we reduce the output variance by accounting for the differences in the input, subtracting them away. And so this is highly desirable when confirming goodness of fit, so because it increases the power of our test. So let's see concretely at what I mean by this. So this is very similar to that homework G3 that you're doing, part 2. And I've got an input data set, call this Monday's data, Tuesday's data, Wednesday's data, whatever. And then I've got maybe average wait time for this customer on Monday, average wait time for customers on Tuesday, average wait time for customers on Wednesday, and so on. And I've fed that data into, so of course it was naturally fed into the real system, and I've artificially fed it into the arena system or the simulated system. Now, I can look at these averages down here, and I am tempted to use a two-sample t-test. I'm tempted to go into JUMP or whatever, load these two columns in, and say two-sample t-test on these two. Are these columns, do they have the same mean? That's what a two-sample t-test would test. But I'm not allowed to, because they were generated with the same input. So each of these two outputs are coupled together. These two outputs are coupled together, and so on and so forth. If I did a two-sample t-test, all of these would be smeared into one z bar, and all of these will be smeared into one y bar, and it would calculate one two-sample t statistic. And that's what I'm not allowed to do that, because they are coupled together. And now JUMP isn't going to know that. JUMP will be happy to do a two-sample t-test on these two columns. But if someone looks at your design of experiments, they'll say, hey, your two-sample t-test, it doesn't mean anything because you didn't operate on the right assumptions. It's just the number, it cannot be interpreted. So what do? Instead of working on these two columns, I create a third column of differences. And this says, okay, so for this input set, what was the difference in performance? For Tuesday's input set, what was the difference in performance? For Wednesday's input set, what was the difference in performance? And so this makes a lot of sense. So for whatever the challenges were on Monday, like we had some really tough customers on Monday, this is how much better or worse the sim performed. For whatever easy customers we got on Tuesday, how better or worse the sim performed, and so on and so forth. And that gives me a single column. And with a single column of difference data, I can do a one-sample t-test, testing the hypothesis that this difference is equal to 0. And if this difference is close enough to 0, then I can say my sim is equal to the real system. It's a good proxy for the real system. So that's what I'm setting up here. So before I step forward on actually doing that and then doing the power analysis, I want to make sure everybody's comfortable with this setup. Does everyone understand how we went from two dependent columns to one column, and what the heck, like why we did that and what's going on there? Any questions about the general setup here? Online as well. Again, this is basically what you do in part 2 of your homework, G3. Okay. And there's a lot of conceptual questions I can ask about on a final exam. Like, I could tell you that I've produced outputs that share the same input. And I would ask you, what is a most appropriate test to test for means or something like that? And you'd have to know that a two-sample t-test would not be appropriate. So even though there's two columns of data, even though I'm testing for means, do not use a two-sample t-test. Use a one-sample t-test on the differences, or a paired t-test on the differences. Okay. All right, so with all of these, I can calculate a mean difference and a variance of the difference. And my null hypothesis is that if these two systems are the same, then this should be described by a mean of 0. If these two systems are different, then this column should not be consistent with a mean of 0. So I calculate a one sample t statistic where my null hypothesis has got a mean of 0. So it's just going to be the average of this column divided by the standard error of the mean, really. So it's just the average of the column divided by its own standard error of the mean. And that gives me my t statistic. And with that, I can say, you know, are these different or not? Now, it may be that I find out that this t statistic is not, that it ends up not being significantly different. So then before I can report that my sim is good enough, I need to have already done the power analysis, which you do on homework G3, and I'm going to show you an example of in the next slide, to say that for k samples, if this doesn't reject the hypothesis, then we can safely conclude that these two systems are close enough. And I can do the power analysis before I even calculate this, as long as I have an estimate of this standard deviation ahead of time. But so I can't conclude a negative result means anything. So if I conclude that the null is not rejected, I can't actually conclude that it's true unless I've done this power analysis ahead of time. So how do I do that power analysis? Well, before I even can do that t-test, as long as I have an estimate of this variance, I can calculate the effect size. Now, what is the effect size? It's just going to be whatever I call close enough between the means. Like, so if I want to say that as long as my sim is within 1 unit of the real data, that's close enough. I might say it's 10 units is close enough. Or in other words, if my sim generates an average that's more than 1 away, that sim is like a different system and it needs work. So whatever I define as my threshold for close enough, that is the capital D here. And I divide that by the standard deviation in this difference data. And so I have to either already have that available to me or I have to run a pilot study to generate that. And then I can calculate this effect size. And then I have to ask my boss. So my boss already told me what the D function was here, or what the D level was here. I have to ask my boss, what's your desired power? And it usually is going to be 80%. So what we're saying is 80% of the time, we will correctly accept that a sim is the same as the real system when the differences are less than capital D. All right, so I've got my effect size, I've got my power. So what do I do next? I go in the back of the book and I look for operating characteristic curves. And there's going to be operating characteristic curves for every basic statistical test, t-test, chi-square test, or whatever. And the curves will exist for different alpha values. So in this case, we're in alpha of 0.05, so I'm going to zoom in on that one. Now, this is the by-hand way to do it. As I think I'll mention in a slide or two, the modern way to do it is use a computational tool. So inside R, inside MATLAB, inside JUMP, you can already do power analyses. If you really need a fancy power analysis, there are tools like GPower that will do power analyses for even more sophisticated statistical tests. But this is the old-fashioned way to do it, where I've got my effect sizes on the x-axis. I've got my false negative rate, so my type 2 error, on the y-axis. Remember that statistical power is 1 minus beta. Beta's on the y-axis. I needed an 80% power, so I go to a 20% beta. And so basically, for whatever effect size I calculate, so for the effect size of 1, I'll go up to here, And then I'll say, well, how many samples do I need for a 20% false negative rate? And it's going to say that I need, for an effect size of 1, 10 samples or higher. Because if I go higher than 10 samples, I go onto curves that get lower and lower in terms of their beta. So if I calculate an effect size of 2.5, then here I'd say, well, for 2.5, 3 is too little. That's way too high beta. 4 is less than I need. So, so actually 4 is what I'm going to choose for 2.5. So that's how we interpret this table. So it tells you for the desired close enough level, standardized to generate effect size, and a desired statistical power, I now know how many samples I need to take to be able to accept a null, if we want to use that terminology. Questions about this? And this is basically exactly what you'll do in part 2 of homework G3, if you haven't already done it. Questions online? Okay. So like I said, moving forward, after you've done this once by hand, the rest of your career, a computer will do it for you. You know, there's again, MATLAB, R's function is PWR. I think there's a graphical menu of it somewhere in JUMP that'll do power analysis. But in order to really understand what you're doing, I think it's nice to actually do it once by yourself. And that's what I'm forcing you to do on that homework. Okay. So any other questions? Feel comfortable? That's your last hint on homework G3. So you should be all set to turn it in the upcoming due date. Okay. All right, so other things we need to cover here. So we've been talking about a t-test a lot. T-test is what we call a parametric test. And it's parametric because a t-test assumes normality and then makes the inference on the mean of the normal distribution. So it's saying, I'm going to take for granted that the data are normal. If I take for granted the data are normal, I am then now going to infer whether the mean of these normal data are actually what I think they might be. And so I'll assume that the mean is 5. I test, and it turns out that they're far enough away from 5. I have to reject that. But I still got the standard deviation and the shape of the distribution right. But I just made an inference on the parameter of the distribution. And that's why we call them parametric, because we have to assume the shape of the distribution ahead of time. Now, other examples, so students t-test, pair difference t-test, and ANOVA. There's a bunch of examples. Even linear models assume that residuals are normal. And so there's a bunch of cases where we have to assume normality before we're allowed to use the test. And that's the reason why I mentioned to you that things like you need something like a Shapiro-Wilk test to guarantee that your data are normal ahead of time before you even use these tests. If you cannot guarantee that your data are normally distributed, you cannot use a t-test. You have to go and look up a non-parametric test that does the same thing. So, you know, what's the next letter after T? U. A Mann-Whitney U-test is a non-parametric t-test. The Wilcoxon signed rank test, that's the non-parametric version of the pair difference t-test. The Kruskal-Wallis test, that's the non-parametric version of the ANOVA. So we teach you all of the parametric stuff in like 380 and in this class because it's relatively easy. And then I just need to tell you though that in reality, you very often can't use the parametrics. You have to often use the non-parametrics, but that's easy to do. If you forget what a non-parametric t-test is, as long as you remember the word non-parametric, you can Google for non-parametric t-test, and the first link will be Mann-Whitney U-test. And you'll be like, oh, okay, I need to look up the U-test then. And then you'll find it because it's already implemented in JUMP or SAS or SPSS, and that's great. Same thing with all the rest of these tests, already implemented in all the major stats packages. But yeah, so we build your conceptual sort of awareness of these tests with the parametric, but then know that you often have to use non-parametric in real life. So keep that in mind. If we go further and say an exact non-parametric method, then that is like the uber stat that requires absolutely no assumptions in order to use. So so for example, the Mann-Whitney U-test here, that's not testing means. That's actually sort of saying, well, it is sort of testing means, but it's like saying that the median of two numbers are the same, but we're not assuming anything about the distribution. If I look at, say, the chi-squared test, the chi-squared test is a distribution test, saying, did I get the same count that I was expecting? But I assume that the number of bins or the number of expected counts in each bin is at least 5. So a chi-squared test is obviously not exact because I need to make some approximation in order to get it to work. But there are, the Kolmogorov-Smirnov test does not require any assumptions to use. If you need a distributional test, out of the box, you can use the KS test. It might be not exactly the perfect test for you. Maybe it's too high powered or something like that. But it is a test you can always use without having to make any assumptions ahead of time. So that's kind of the sort of taxonomy of these things here, is that you have parametric tests that have high power because they assume something. You have non-parametric tests that generally have less power. And then you have exact and non-exact non-parametric methods, which may or may not require some assumptions, but they don't make distributional assumptions. So that's kind of the categories here, and I'll use some of these words kind of throughout. So, so any questions about that? What I mean by parametric and why the t-test is a parametric test? So more just basic stats vocab that you could imagine me asking about, like, you know, pick the parametric test out of this list, that sort of thing. Okay. So how the heck does a chi-squared test work? I didn't quite get to this last time, but I've got kind of the summary here. Chi-squared test works effectively the same way as a t-test, but it's testing a different thing. Instead of testing whether two means are the same, it's testing whether two distributions are the same, an observed distribution and an expected distribution, and it calculates a stat based on that. So how does it work, and why do you need 5 expected in each bin? Well, if we think about a single bin, if we think about the probability that something should be in a single bin, so we have like 10 bins or 10 classes, and we have, you know, so many are supposed to land in each one of those 10. Well, so the idea here is you could say, well, there's some probability, let's say it's a 5.5% probability that the outcome should land in this particular class, in this particular bin. And I have 100 options. And so those 100 are going to land in all of these bins, but 5.5% of them are going to land in this bin. Well, forget about the chi-square test. Just think about a binomial test. In a binomial test, I get a distribution here. So this is a binomial, the probability mass function for a binomial. So for 100, 5.5% are in, and the other, all the rest of the 94.5% are out. And so this is the distribution of how many will be in the bin. And the expected count in this case is about 5.5. Okay, so that's for a binomial. Now, if you look at this binomial, it looks kind of bell-shaped. And a lot of counts-based distributions will look bell-shaped because of the central limit theorem, so long as the expected count is high enough. So let's drill down on that and think about it a little bit more. What if the probability was smaller so that the expected number that would fall in the bin were like 1? Well, this is what the binomial would look like. And it still has a hump, but it's pretty much, it's almost like an exponential, really. Like it's really asymmetric. If I extend that so the probability is a little higher, so the expected number are 2, again, it kind of looks like a bell curve, but it's like it's chopped off on the left, it's truncated. I can keep doing this game and I can make the expected number in the binomial higher and higher, and it doesn't really start looking like a decent bell curve until about 5 land in the bin. And that will end up being the key to why a chi-squared test requires the expected number in each bin to be 5 or more. A chi-squared test replaces a binomial distribution with a normal. And you can only do that if the expected value of the binomial is 5 or more. And that's the reason why in a chi-squared test, every bin has to have at least 5 or more, because otherwise you can't replace it with a normal, and the whole chi-squared math depends on using normals. But I can drill down on a little bit farther and say, if I've got n greater than or equal to 5, so if I've got the expected number in each bin, so I guess I should have made this np. So if I had the expected number in each bin to be greater than or equal to 5, then I can create this variable called chi. And that chi is just a standardized, it's a standard normal. It's a standardized version of what lands in that bin. It's the observed number in the bin minus the expected number in the bin. And the variance of a binomial distribution, if you look it up, is the thing under the square root here. So this chi is just a standardized difference from the expectation of a binomial. In pi, that's for a probability, in bin I, the probability of landing in the bin is pi. In pi is the expectation of landing in the bin. OI is the number observed landed in the bin. And then I take the square root of the variance, and that's how I get my standard deviation. And as long as the NPI is greater than or equal to 5, then this chi is approximated by a standard normal. Bonus, if you square this expression, there's this convenient mathematic, you can just kind of do a little bit of replacement, and it turns out that this single standard normal squared, you can rearrange it a bit, and it takes on this form. And that form should look familiar to you. That's the chi-squared formula for 2 classes. So there's your class 1, there's your class 2. So remember the chi-squared, I told you the chi-squared is the number, the degrees of freedom are 1 less than the number of classes. Well, that's also where this comes from here. What I'm saying is if I have 2 classes where the observed number in class 1 are represented by this term, and the observed number in class 2, all the rest, are represented by this term, then that thing together is actually just the square of a single standard normal. So it looks like I've got 2 terms, but it's really 1 standard normal squared. And so that's why a chi-squared, if I look at the number of degrees of freedom, a chi-squared is just the sum of that many standard normals. And so if I look at this yellow line here, this is degree of freedom equal to 1. This is what happens if you take a standard normal and you square it. That basically turns all the negatives into positives, and it raises the peak up, and you get this kind of ski slope thing. Turns out if you add 2 standard normals together and square them together, you get an exponential. And that's another cool factor we can use for other interesting things. If you add 3 standard normals together, squared, you get something that starts having a hump. And by the central limit theorem, not surprising, as you add 9 standard normals together, squared, each one of them squared, you get something that starts looking like a normal distribution itself. So not surprisingly, in these, that we've got yet another statistical quantity that as the degrees of freedom goes to infinity, it becomes more and more like a normal distribution. So that's where this comes from. It's just every chi-squared is like the total squared z-score under a null deviation from each one of its bins, where you think of each bin as a binomial variable being approximated by a standard normal, which you can only do if the expected number in that bin is 5 or higher. And as we get more and more bins, what I've plotted here is the chi-squared test statistic and the corresponding p-value. And each one of these are the number of degrees of freedom. So if I go down to 0.05, then what this is telling me is as I add more bins, I tolerate higher and higher values of the chi-squared statistic. So in other words, I'm just accumulating error. And so if I've got lots and lots of bins, there's lots and lots of opportunities to be different from expectation. And that's why the critical chi-squared value goes up as the degrees of freedom goes up. So that's the background behind the chi-squared test and why you need 5 or more. So the big thing I want you to take away from it is just that this, this restriction of 5 or more is a so-called continuity approximation. It's approximating a binomial by a normal, and you can only do that if the mean of the binomial is 5 or more. That's where the 5 comes from. And if you want to see what that looks like, I basically generated a null distribution, and then I perturbed it a little bit. So my null distribution generates chi-squared values that look like this dotted line. And then I perturbed it a little bit, and I generated data in a slightly different distribution that's pretty close, and that's the histogram here. And then I perturbed that a little bit more to generate another set, generate a data in bins with a slightly different distribution, and that gave me this histogram here. And so as you're seeing that this is the critical chi-squared value here, that as the distribution gets farther away from the null distribution, then more and more outcomes from calculating the chi-squared get to the right of the critical chi-squared value, and thus will be rejected. So this looks just like a t-test, but it's one-sided. So it's just getting your chi-squared values start at 0, and we're not expecting any chi-squared values larger than this. So as the distribution gets farther and farther away, you get chi-squareds that are less and less likely. So that's our chi-squared. All right, so any questions about that, about the foundations of the chi-squared? Again, the big thing I want you to carry away from that is that just to burn into your brains that you need 5 or more to use a chi-squared. And it's all about binomial to normal approximations. Okay, so this chi-squared, that's what a non-parametric test, but it's not exact because it requires this expected value to be 5 or more. If you can't hit that target, but you really want to use a chi-squared for some reason, then there are corrections. So the so-called Yates correction for continuity allows you, for a small number of classes, to continue to use a chi-squared, even though this approximation isn't there. It's really ugly, and no one trusts anyone who uses Yates. It's usually a red flag for a bad statistician, but there are plenty of bad statisticians out there. If you would like to be one of them, you can use Yates. You won't get fired. A lot of people use it. A better alternative is to use the G-test. So a G-test is like somebody re-engineered the chi-squared test years after the chi-squared test and allowed it to work pretty much identical, but with an expected count, you can get much weaker requirements. If worse comes to worst, what you can also do is actually go to truly exact tests. Like if you have a small number of classes, the chi-squared test is effectively an approximation of a binomial test. Just use a binomial test if you only have 2 classes. If you have more than 2 classes, there's something called a multinomial test. And it's basically an exact version of a chi-squared test. There's also something called Fisher's exact test, which again can be viewed as an exact version of the chi-squared test, but it really only is safe for small numbers and has very low power. So it can be kind of overly conservative. So, if this is one of the things where if you can use a chi-squared, the chi-squared is generally going to be a better test to use. But if you can't, there are alternatives. And of course, there's also the Kolmogorov-Smirnov test that we've talked about. Okay. So any questions about any of that? I'm trying to help you build this kind of decision tree of which tests to use and when. All right, and then I mentioned the Kolmogorov-Smirnov test. So if you're doing goodness of fit tests, again, also remember, use your QQ plots. But then this KS test, it's an exact test, no assumptions required, measures the difference between sample and hypothetical. There's also a 2-sample version measuring whether 2 distributions come together. Well, how the heck do KS tests generate their statistics if they have no assumptions? And the way a KS test works is by using something called a Brownian bridge. And it's a really cute idea. It's this idea that if you were, if this red line is your expected CDF, and this blue line is the empirical CDF taken from data. We know that those two CDFs must end at the same point. We know they must start at the same point. And so what that kind of means is that there's going to be variation in the middle. And what we imagine that we were just taking random movements from this point where they both start away from that point, knowing that we're going to post-select for movements that eventually land at the same point here. So it's like a drunk who knows where the bar is and knows where home is, and they do a drunken walk, and they always are guaranteed to get home. But we study how far away they get from the shortest path. And we know that if they get very, very far from the shortest path, then maybe we actually don't have the shortest path. So we're sort of under the assumption that a drunk is going to have a variation around the shortest path getting home. And but if we're assuming that that we've got the right shortest path, and so if they vary too far from it, then maybe we've got the wrong guess for what the shortest path home is. And this is a so-called Brownian bridge, where we can actually study what's the probability that such a drunken walk, so that's what another name for Brownian motion, would get this far away. And that's where you get the critical Komarov-Smirnov values here. So it's just sort of assuming that if you talk about a process, it starts in a point, it ends in a point, how far away can it get from an assumed kind of shortest path, if that truly is the shortest path between them. So that's the so-called Brownian bridge. So I can take this and I can imagine it's smeared so that I've got like, they start at 0 and they end at 0, and you can just see like sort of how far away can it get. So if you can only take n equals 5 steps, how far could you possibly get away? And if you get farther than that, then you probably are walking along a different distribution. That's kind of how the KS test works. And the other tests we've talked about, I'm not going to talk about the mechanisms behind them, but you should know that Anderson-Darling is a nice alternative to KS, extremely powerful. And if you have to test for normality, just go to the Shapiro-Wilk test, because it is extremely high powered, but it's only used for normality. So after this class, when it's really important for you to test for normality before you do a t-test or an ANOVA or your linear modeling, do the Shapiro-Wilk first. I'm not going to beat this over your heads in assignments in this class, but I really want you to know that you can't just haphazardly use a t-test out in the real world. You've got to do a Shapiro-Wilk first. All right, so any questions about any of that? Questions online? Okay, so the last thing I want to kind of mention that we skipped over last time. So we've had this picture so far, our input variables, our decision variables, our outputs. So the question comes be, we have multiple outputs. So here we got teller's utilization, average delay, maximum line length. These are all performance measures that I could measure simultaneously. And so the question is, if I'm trying to tell the difference between an as-is system and a hypothetically improved system, where do I look for the improvement? Do I look for it in output A, output B, output C, all three of them? What if output B shows an improvement, but outputs A and C don't show any improvement? How is that different than when all three show an improvement? What could go wrong? And what you have to realize here is if the more outputs you add, your false positive rate ratchets up, because you have a 5% chance of detecting an improvement here that's not an improvement. You have a 5% chance of detecting improvement here that's not an improvement. You have a 5% chance of detecting improvement here that's not an improvement. So if you said, I'm going to look at all three, and if any one of them improve, I'm going to call that an improvement, then you're running the risk of detecting an improvement that's not actually there. It's the fishing problem, or known as the multiple response problem, or the multiple comparisons problem. So we have a fix for that. There's a lot of more sophisticated fixes, but the simple fix that we talk about in this class is what's called the Bonferroni correction. And all it is for each of your individual tests, you have to adjust their false positive rate so that they're much lower, so that the family-wise false positive rate is what you want it to be. So this is me kind of saying that mathematically. The probability of at least one false positive in multiple tests is going to be basically one minus the probability of false positive in each individual test. So as the K individual tests go up, then the probability of a false positive across any of them goes way higher than the desired false positive rate. So what we do conservatively is across each individual test, if I want a 5% for all of them, I test each individual with 5% divided by the number of comparisons. So in this case, if I'm doing 3 comparisons, like I'm going to compare utilization across A and B, delay across A and B, and maximum line length across A and B, those are 3 comparisons. So in that case, if I want a 5% error rate, each one of those individual t-tests is going to need to use a 5 divided by 3 alpha. So you actually have to adjust the alpha on each individual test so that the test as a whole has the desired alpha. And that's the Bonferroni correction for multiple comparisons. Are there any questions about that? So this comes up a lot because you're going to have a lot of different output variables. And when you're presenting your work at the end of the semester, you don't want to say, we did these 10 tests and it looks like we got one of the 10 ended up showing a significant difference. So in that case, we made a major improvement in the system. That's you probably just were fishing. Now, if you can tell me that of those 10 tests, then you detected a difference, even though each individual test had an alpha divided by 10, then I believe you. But if each one of those individual tests had an alpha of 5%, then the whole group as a whole, the fact that you found any difference whatsoever is going to be much higher than 5%. That makes sense. The multiple comparisons problem and Bonferroni correction. Okay. So in the real world, there are more sophisticated options, MANOVAs, ANOVAs with so-called post hoc tests. So look out for those. But before you start, taking a more advanced stats class where you've got things like post hoc tests and multivariate ANOVAs, then this is a great way to go. Nobody's going to complain if you do a Bonferroni correction. It's a little conservative, but it is totally legit. All right. So as I mentioned at the start of last lecture, with the kind of Ghostbusters example, alpha equals 0.05, that's going to be the traditional rate that we assume. But when you get into real applications, where you've got real R&D money to throw at things, a lot of times you really do want to detect a small difference. And you're okay with maybe falsely detecting a difference because if that small difference has the opportunity to give you a competitive advantage with a little more engineering, then you want to further investigate that. So a lot of times when we screen for differences in engineering, we effectively choose an alpha of higher than 0.05. But for just to kind of keep things consistent with science in general, in this class, we're going to keep it at 0.05. But we actually tolerate much higher false positive rates in engineering R&D because we're looking for competitive advantages. So, and that's all I'm kind of summarize here. Questions about that? All right, great. All right, so like I said, this is sort of a brief intro lecture for Unit J. The meat of it's going to come in the next 2 lectures on transient systems and steady state. So the main things that we're focusing now, we're shifting from input to output. So we need to ask questions like, which measures of performance should we base our decisions on? How do we complete our simulations quickly and still be useful? And how do we reduce bias? And what the heck is bias while also trying to reduce computational time. So we get into that here throughout the rest of the unit. And so we'll define all of those sorts of things. And the first things we need to define are the types of systems that we are going to simulate and the types of simulations that are matched to those systems. So there are two types of systems that we focus on: terminating and non-terminating systems. And I'm going to define those in a second. And terminating systems are simulated with transient simulations, and non-terminating systems are simulated with steady state simulations. And we'll define that here in a second. So a terminating system is a system that has a defined end time that's kind of defined by the system. So it could be a length of time, or it could be a time when a particular condition is met. But we know that that condition will eventually be met. Like eventually there will be no customers left at the door. And whenever that happens, that happens, but we know that every day, eventually there are no customers left. So, so this terminating system is a system that has a clear defined, Monday, Tuesday, Wednesday. It doesn't run forever. And we simulate terminating systems by so-called transient simulations. Oftentimes these words are synonymous. I'm totally happy if you're going to interchange them. If I use them, though, I want you to sort of make sure that you recognize how I'm using them. But if you want to say terminating simulation or transient system, that's usually totally fine. Example here, a bank, it opens and closes every day. It always opens at 8:30. And at that time, it's a normal event that there'll be no customers there. That's not just a weird artifact of the sim. There really are no customers at 8 a.m. In the bank. And the bank always closes at 4:30 p.m. So 480 minutes later. And that always happens that way. So we always have a start event with certain start conditions. That's part of the real system, and an end event with certain end conditions. That's part of the real system. So we're modeling the bank as a terminating system because we're focusing on a single day's operation. It begins and ends. So in Arena, so this is an example that I think you'll see here, or you've already seen this call center example. And this is one case where it ends, but it doesn't end at a concrete time. It ends when all the customers clear the queue. And so in Arena, under the run setup, it looks a little different in the latest versions of Arena, but there's still a replication parameters tab. And when you go to the replication length, you can set it to infinite. Now, it's not actually infinite, because you go down here, and in this call center example, if you're to open that one up, I think it's one of the ones provided with the book, then the terminating condition is set. And it basically says that it will either end when there is a particular time hits the clock, or the number of callers in the trunk, and the number of callers in the trunk is equal to 0. So if the trunk line still has callers on it, the system stays open, but eventually those callers go to 0. And if that happens after the specified end time, then the call center closes. It may close after the end time, but it definitely closes. So we can define either end times or end events, but the call center always closes. We can contrast that with a non-terminating system, which runs for a relatively long period of time that we approximate to be infinite or basically continuously. So we study the steady state properties of the system. We do not focus on the initial conditions. So even though the real system opened at one point, it's been open for so long that its operation doesn't have any influence from the opening conditions. So we forget about them. We don't need them. So, so that's what we're sort of saying. There's an initial and stopping time that have no real meaning in the real system, but they have to be implemented in our simulated system because our simulated system can't run forever, and it has to start at some point. So we have to carefully pick our initial conditions so as to not screw up the steady state. And we have to carefully pick our stopping time to ensure that we analyze the part of the system after the initial transients have died out. So examples, assembly lines that shut down infrequently, that are effectively 24/7. telephone systems that are effectively 24/7, emergency rooms, 24-hour grocery stores. In real life, all of these things do shut down, but they shut down so infrequently that as an operations researcher, we don't really care about that. It's so rare that, yeah, you'll shut it down, it'll be down for a certain amount of time, it'll come back up, it'll be a little awkward for a day or two, and then it'll be back to normal. So we focus on the normal, we don't focus on the shutdowns there. We cut kind of those things out. So with that in mind, I can kind of look at this, roughly the same trajectory here, but viewed as either a terminating or a non-terminating system. In the terminating system, the bank opens, there's no customers, and so the wait time is 0. Now, once customers start showing up and queuing up, the wait time rises, and then eventually there's sort of a general kind of steady state wait time for the rest of the day, but eventually the bank closes. And if I want to know what the average wait time was for customers, I include all of this trajectory. So I include the fast customers in the beginning as well as the slower customers towards the end. That's a terminating system. It's also called a transient simulation because I care about the transients. I include them in my stats. Now, if it's a steady state, let's say this is instead not a bank opening up. Let's say it's a Walmart, a 24/7 Walmart opening up. Now, I have to start my simulated Walmart somewhere. I start it up and there's no customers in the Walmart. And over time, we start getting customers in the Walmart. And so eventually I get some customers in the Walmart. But in the real Walmart, you go into any Walmart, there's always sort of a background level of customers in it. It's never totally empty. And so the artificial case of when the Walmart's totally empty, that's just something that existed temporarily in the computer. So what I'm going to do is set I'm going to set this period here where I'm going to truncate these data. So I basically forget about these data. I can tell Arena that there's a warm-up period where it should not include data from, say, 0 to an hour in any of its calculations. Just throw them all away. And you'll see this in Lab 9. And then it starts taking data after this. And that will end up being our steady state simulation because we're focused on just the steady state, not the transient. So the transient simulation, we care about everything, including the startup transient. The steady state simulation, we only care about the steady state. We throw away the startup transient. All right, so any questions about this distinction? Terminating, non-terminating, transient versus steady state. A lot of times it'll be the exact same model, but it's just the way you set up the run inside Arena. Okay. All right, so I would do an attendance question here because I had to kind of cover some of that stuff we missed last time. I'm going to skip over that. I want to cover a couple other little intro things here. When we run our sims, as you'll see in Lab 9, we can have 3 replications. So that's what I've got in columns here, 3 independent replications, different random number seeds. But within every replication, I can have this replication run very long, and I can batch certain time intervals. So from 0 to 1,000 minutes, I create a batch. And what do I do with that batch? I might calculate an output measure just for that batch. Then from 1,000 to 2,000, I calculate an output measure just from that batch, and so on. So in one replication, I can either get a number out of the whole replication, all 5,000 minutes, or I can get 5 numbers out of this one single replication. And then across replications, I can get numbers out of each replication. Then I also get 5 numbers per replication. So what I'm interested in is, where is the independence? I know that I've got independence from one replication to a second to a third, but maybe I can get away with running a single replication, but instead cutting up the data from that replication so that each one of these little sub measures ends up being independent from the others. So it's like running one replication is like generating 5 independent replications out. So I need to know, can I really count on these things being independent from each other when I get independence across replications for free? So what we're going to see as we move on in the next 2 units is that if you can do things within replications, it's going to be computationally cheaper, but you always run the risk of your data losing its independence. And that is going to be a major problem for the stats, because the stats that we use are built on independence. So within replication are not necessarily independent. Across replications are always independent. Okay, so our objective is to estimate performance, do the sim. We have some parameter like the average waiting time for a customer. We have to estimate it from samples of simulation output, because every time we run the sim, we get a different set of customers, and so we get different waiting times. So we are going to start by designing a point estimator of our performance parameter. So this will be an estimate of the average waiting time for the customer. So it'll be, every time we run a new experiment, we might get a new estimate of this performance parameter. And so that's what we have to, this point estimator's got this problem that we can't really trust it, because if we rerun the experiment, it might give us a different estimate. So we need to understand how the estimate moves around relative to the actual parameter we're trying to estimate. So when each sample comes from a different simulation run, then we're going to call each run of the simulation a replication. So replication implies independence. So I'm going to commonly use capital R to represent the number of total replications instead of N or capital N or whatever. Whenever possible, I'll try to use capital R. So lowercase n, whenever possible, I'll try to save for data collected within a replication, and capital R across replication. So cross replication data are independent, generally identically distributed because it's the same sim after all, and often normally distributed because often the parameters that we get out of them are sums. And so we depend on the central limit theorem to give us normal distributed. So that means that these are really great for things like t-tests. So that's another reason why I don't worry so much in this class where you're running Shapiro-Wilks, because most of the data that you generate with sims are going to naturally fit all of the assumptions of a t-test. So as an example, I might take the sample mean across replications. So each replication generates an average waiting time for customers on that day, like Monday, and then the next replication is Tuesday, and so on. And so I've got my sample mean from these R replications. Because the observations are independent, we can calculate a standard error of the mean. And this will tell me that if I rerun the experiment, what's the spread of the sample mean? So that if I rerun the experiment, the sample mean is going to shift. Well, the standard error tells me how much that mean is going to shift. And so, so I can calculate that standard error, again, using this formula here, where R is number of samples. So I hope you can see that if I increase the number of replications, the standard error goes to 0. So your point estimator becomes almost exact if you can run an infinite number of replications. The problem is, under limited computational budgets, we're going to run very small numbers of replications. So that's going to mean that every time we rerun our experiment, then we're going to get different values for y hat. And so that's what we need to kind of capture. So the other things we have to worry about is say, well, if we want to take data within replication, what's the downside of doing that? The samples we take within a replication may not be independent. For example, if I'm simulating an inventory system, the inventory for 1 week is likely correlated to the inventory numbers for the next week. So it's difficult for us to use these data because most of our statistical tests require that each sample be independent of all the other samples. And we don't get that if we're taking samples within a sim, within a replication, a single replication. As I hinted to before, we can create batches, and if those batches are really large, they'll become far apart from each other, that hopefully they generate independence. And that's kind of what we talked about here, where I can create batches, and then from within a replication, hopefully this batch is so large that the average from this batch is going to be independent of the average from this batch. And so a key question that we'll have to get to in 2 lectures is how do we decide how big to make these batches to ensure these are independent? Because we'll see it's going to be cheaper to generate data within 1 replication than it is to generate data across replications. And then the other problem that we need to deal with, and this is, I'll let you go right after this, is initialization bias. And so this is, I've already kind of showed you that if I include in a transient simulation, it includes the transient, but if I'm trying to estimate a steady state and I include those transients, which are not real, then these data will pull down the actual estimate so that I create a bias. And I'll go ahead and redefine bias next time. So let me get you out of here. So I'll get to the next attendance example right here. And the question that I've got for you is, what do you call a statistical test that makes an assumption about the data has to have a certain distribution in order to use it? So what is the statistical what is a statistical test? Not A, but what do you call a statistical test that requires you to use a particular distribution of data before you can even apply the test? And I would type that into Zoom, but my, oh, there it goes. But my Zoom is sort of not responsive. So those online, hopefully you heard that. What is the statistical test? What is the category of statistical test that requires you to assume a distribution of the data before you can use it? And that's all I've got for you. So we'll see you Thursday for J2. If you have any questions, feel free to come up and I can talk to you after. Okay, those online, if you can still hear me. My Zoom is not really responsive. So I am going to close the room. If you have any questions, please feel free to reach out after.